All right, let's dive in. Today, we're going to tackle a skill that is absolutely essential for anyone who works with Linux. We're going to take a brand new, totally raw disk and turn it into a useful, permanent part of your system. Let's get to it. So, you've just plugged a new drive into your machine. It's just sitting there, full of potential, but as far as the operating system is concerned, it doesn't even exist. We're going to walk through step by step how to bring that drive to life and do it securely and reliably. Okay, our very first step is to create something called a file system. Now, if you think of a raw disk as just a giant, empty warehouse, the file system is the blueprint for how everything gets organized inside. It's the shelves, the aisle markers, the whole inventory system. Without it, the disk is just a big, unusable box. To create that file system, we're going to use the mkefs command. This tells the system to format the disk located at dev/stb with the classic x2 file system. It's a really simple command that lays down that digital blueprint we were just talking about. And this is a huge but, this is a command you have to be extremely careful with. I cannot stress this enough. This is a critical warning. When you run mk2fs, it is a one-way trip. It will obliterate everything on that disk, and there's no going back. So before you even think about hitting enter, you need to be 100% sure you've got the right device. You know, a great habit in system administration is to verify your work right away. Act, then verify. So after running that format command, we can use block ID. This command goes out, asks the disk for its ID, and confirms its new identity. You'll see it gives us a unique ID, the UUID, and that its type is now X2. Perfect. Great, so our disk has a file system, it has a structure, but we still can't actually use it. For that, we need to mount it. The best way to think about this is like adding a new room to your house. The disk is the new room, and the mount point is the doorway you cut into the wall to actually get into it. So let's walk through it. A temporary mount is a super simple three-step process. First, we create our doorway, which is just a directory. We'll call it /test. Second, we use the mount command to connect our disk /dev/stb to that new directory. And third, we verify again with df-th to see our new file system listed and ready for action. Mounting the disk is a great start, but we can do better. We can set specific rules or options that control exactly how the system is allowed to interact with that disk. This is a really powerful way to boost both security and performance. Here are some of the most common options you'll run into. You can make a disk read only with RO. Or, and this is a fantastic security practice, you can prevent any programs from being run from it at all with no exec. This is absolutely perfect for drives that should only hold data, like documents or backups, not actual applications. Let's see that no exec option in action. We use the same mount command as before, but we add that little -o flag, followed by no exec. This is us telling the system, hey, go ahead and mount this disk, but do not, under any circumstances, allow any file on it to be executed as a program. And this just illustrates the power of that option perfectly. Here, we've copied a standard system command, ifconfig, right onto our new drive. But when we try to run it, nope, permission denied. The rule we set at the file system level completely blocks the action, even if the file's own permissions say it's executable. So cool. Okay, so far, our mount is only temporary. If we reboot this machine, it's gone. To make it permanent, we need to edit a really critical system file called /etc/fstab. You can think of this file as the system's startup checklist for every single one of its drives. Now, we can't just tell fstab to mount dev/stb. Why not? Because that device name, well, it isn't guaranteed to be the same after a reboot. Instead, we need a permanent unique ID, and we can get that again with our trusty blkid command, which gives us the disk's unique UUID. Using the UUID is, frankly, a non-negotiable best practice. Device names like SDA, SDB, they can get shuffled around by the kernel when the system boots up. They're not stable. Using the UUID ensures your system always finds and mounts the exact right drive, which helps you avoid a whole world of startup problems. At first glance, a line in the fstab file can look pretty intimidating, but let's just break it down. It's really just 6 fields, each with a clear job: which device to mount, where to mount it, what's its file system type, what options to use, and then 2 flags for system maintenance. It's perfectly logical once you see it laid out like this. And here's why we need to be so darn careful. A typo, a wrong UUID, an invalid option, any little mistake in your etc/fs tab file is one of the most common ways to end up with a system that just won't boot. The stakes are definitely high when you're editing this file, but lucky for us, there's a safety net. And here it is, the mount a command. This command is your best friend. It tells the system to read the /etc/fs tab file right now and try to mount everything listed that isn't already mounted. If there's an error in that new line you added, it will fail right here and you can fix it. You must run this command before you even think about rebooting. We have formatted, we've mounted, and we've made our disk persistent. The final piece of this puzzle is just a bit of maintenance. We need a way to check the integrity of our file system for any errors. And for that, we use the Filesystem check tool, FSCK. Here we go, our final critical warning. You never run a file system check on a mounted file system. It's like trying to perform open heart surgery while the patient is running a marathon. It's a terrible idea. Checking a live, mounted file system can lead to some really severe data corruption because the tool and the system are literally fighting over the data. The correct and safe procedure couldn't be simpler. First, you have to unmount the disk using the unmount command. This takes the file system offline nice and cleanly. Only then is it safe to run FSCK on the device to perform that health check. And here's a quick little cheat sheet to pull it all together for you. From creating the file system with MKE2FS all the way to checking it safely with FSCK, these are the core commands you'll be using again and again. So, if you remember nothing else from this explainer, please remember these 4 golden rules. Always use UUIDs for stability. Always unmount before you check. Always test fstab before you reboot. And use security options wisely. I promise you, following these will save you from 99% of common file system disasters. And there you have it. We've taken a raw disk and turned it into a secure, reliable, and permanent part of our Linux system. You now have the fundamental skills to manage storage like a pro. The only question left is, what awesome projects are you going to build with it? Thanks for joining me.